Hi class. Today you should have picked up your new yellow packet. We're starting the rest of topic 2, and we're starting today with both rotational and reflectional symmetry. After today's video and lesson, you can start on your homework pages 8 and 9. So for this warm-up, you are to basically name all of these polygons based on the number of sides that the polygon has. And the video should be paused now so that students can complete the warm-up. When you look at a three-sided figure, everybody knows that is a triangle. We've dealt with that a lot, even in the last 2 packets. 4 sides is a square. We're talking about regular polygons, and regular polygons are have the same sides or the same length sides, and so therefore, if we're talking about a 4-sided figure, it would be a square that has 4 equal sides. Pentagon is 5 sides. Hexagon is 6. Heptagon is 7. 8 is octagon. 9 sides is nonagon. Decagon for 10 sides. Hanagon for 11. Dodecagon for 12. 13 is tridecagon. And any n sides in a regular polygon, we say n-gon. So please hit pause again so students can write down some of these more unfamiliar names. As we continue on page 5, when we are talking about regular polygons, we are talking about polygons that have, there's that word again, congruent sides and angles. The center of a regular polygon is the center of rotational symmetry. So that's the point where we are rotating our regular polygon. And that center is equidistant or the same distance from each of the vertex. It says from each vertex, so each of the vertices. So here's the center, and each one of these is our vertice. So equidistant, so you can see the congruency marks for each of these line segments. And you can also see the congruency marks on each side of the regular polygon. This one is 5-sided. So we know that the sides are congruent and the segments connecting the center are congruent. The central angle of a regular polygon is equal to the degree of rotational symmetry. Now, we talked a little bit about rotational symmetry in the last packet, and we were mostly talking about how many times we had to rotate the figure to get the same picture again. So if we're looking at our pentagon, we see that if we rotate it 5 times, then we get the same picture of that pentagon all 5 times. If I'm going to get the measure of that angle, that central angle, what I'm going to do is I'm going to take all the degrees in my polygon, and I'm going to divide it by the number of sides. So if I go all the way around clockwise or counterclockwise on any polygon, that's 360 degrees to make a full circle. In this case, I have 5 sides. So the central angle is 72 degrees. So if I'm to do any central angle of a regular polygon with n sides, meaning it doesn't matter how many sides it has, I'm going to do 360 degrees divided by n, the number of sides. You can pause here if students need to write this down. Okay, so moving on to more information about rotational symmetry. A figure has rotational symmetry if and only if it has at least one image, not counting rotation image of 0 degrees. So that means the starting point or the pre-image does not count, nor does a full circle around. So when it talks about multiples of 360, that includes one full circle around, or two full circles around would be 2 times 360. So this is what coincides with the pre-image. So that means I get the same picture of the image that I had with the pre-image, and I don't count the very first picture, and I don't count the very last picture, especially if it only goes around one time. The number of positions in which the object looks exactly the same is called the order of symmetry. And we did a little of that in our last packet. The measure of the central angle of a regular polygon is called the degree of symmetry. So that calculation we did before gave us the degree of symmetry, because that was the measure of the central angle. Okay, so for our rotational symmetry, we are trying to calculate both the order of symmetry. So as we rotate it fully around 360 degrees, how many times does the polygon map onto itself? There's that word map again. So it's basically mapping the pre-image to the image. And then also for every one of these polygons, the degree of symmetry or the measure of the central angle. So we can see with a triangle, especially a triangle that is equilateral, meaning 3 equal sides, I'm going to rotate it 3 times and get the exact same looking triangle. Same thing with a square. 4 sides, 4 rotations. Pentagon, 5 turns gets me the same mapping of the pre-image or the image to the pre-image. Happens 5 different times with 5 different turns. It's going to be 6 for a hexagon and 8 for an octagon. So equal to the number of sides. The degree of symmetry is going to be all of these orders of symmetry divided into 360 degrees, because that's what gives us the central angle. So 360 divided by n, and that's 360 degrees. And we'll let our order of symmetry basically be n. So for a triangle, 360 divided by 3 is a degree of symmetry of 120 degrees. 360 degrees divided by n, or 4 for our 4-sided square, 90 degrees. 360 degrees divided by 5, 72 degrees. 360 divided by 6, 60 degrees. And last, 360 degrees divided by 8 should be a central angle or degree of symmetry of 45 degrees. So in case you haven't done that already, you can also pause the video again to write in these order of symmetries and degrees of symmetry. Okay, moving on to reflection symmetry on page 7. A figure has reflectional symmetry if and only if the image reflected across a line coincides exactly with the pre-image. This line is called the line of symmetry. So we were talking before in the last packet about a line of reflection. Now we're talking about reflectional symmetry. So we are calling it the line of symmetry. And in each of these pictures with the dotted line, you can see that line of symmetry. The line that divides our figure in half, so it's almost like a mirror where one half of the picture looks exactly like the other half of the picture. Same with our triangle. And with our letter E, if we go this way to draw our line of symmetry, and we can see with our diamond shape, we can go both ways, two different lines to get our two different lines of symmetry. Now, for the next figures, determine and sketch the number of lines of reflectional symmetry for each of the regular polygons. So I want to know how many lines I can draw in order to get that perfect mirror image. So let's start with our triangle. If I go straight down the middle, I get two halves that look exactly the same. If I go through this side to the vertex, I also have two sides of the triangle that look exactly the same. Lastly, I can draw that third line. Now you should be seeing a pattern here. 3 sides, 3 lines of reflectional symmetry. So we'll look at our square. It has 4 sides, so how many lines should I be able to draw? Let's see. 1 cuts it in half. 2 cuts it in half the other way. 3 cuts it on diagonal. I still have 2 equal sides on either side of the line of reflection. 4th line also cuts it in half, perfectly equal sides. And we can imagine with our pentagon, the same thing's going to happen. 1, 2, 3, 4, 5. If you look carefully at all of those different lines, they also cut that pentagon into 2 equal halves. Okay, last bit before you can work on your homework. I've got 6-sided figure and I've got an octagon on the right. So if we draw our lines, and you can pause the video to do so, please draw the lines of reflectional symmetry for each of those regular polygons. When you're finished drawing them, you should see that this hexagon has 6 lines of reflectional symmetry. 1, 2, 3, 4, 5, 6. And our octagon is going to have 1, 2, 3, 4, 5, 6, 7, 8. So the number of lines of reflectional symmetry are going to be the same as the number of sides. And remember, this is for a regular or equal-sided polygon. Thank you for listening. Please do your homework on the next 2 pages, 8 and 9, and we'll see you tomorrow.